Okay, the next one is on properties. So, the next part of the talk will be on the properties of ultra high performance concrete, and I will show you only a few properties of interest. So, let us talk about compressive strength. Now, if you just do a simple compressive strength, you will say that I have 150, 160 megapascal strength. But like I showed you earlier, the reason why we use ultra high performance concrete is not just for strength. Strength is one thing, but we also want to know how we can use this material in designing structures. So, if you do design of reinforced concrete structures like bridges or girders or columns, you actually want to know the complete stress strain response, right, and not just the complete stress strain response, axial stress, axial strain, you also want to know the lateral response. So, now the testing has to account for both the axial deformation and the lateral changes in dimension. Make sense? So, you have to do both axial and lateral. So, if you have to do that, and so we are doing this in displacement control mode in a closed loop testing with a radial strain control, because your radial strain is much more, your overall volumetric strain is axial strain plus twice the radial strain, right. So, your radial strain is very sensitive, and therefore, you have to control the radial strain after you have loaded to about 50% of the peak. So, there are a couple of different load changes that you have to do in this kind of testing, and we did ultrasonic pulse velocity testing as the specimen is being loaded, so that we can do non-destructively the elastic modulus under different loading stages. Okay. So, here is the complete axial stress, axial strain and axial stress radial strain curves for unreinforced, non-fiber reinforced UHPCs. You see this maximum strength of 150 megapascal, the maximum axial strain of about 0.3, 0.35%, which is 0.003, right, which is basically what you say is the maximum allowable strain of concrete in design. So, first understanding, ultra high performance concrete does not change your maximum axial compressive strain capacity of concrete, okay, in unreinforced state. The strength you can see up to 160, 170 megapascal strength depending on what kind of mix it is, and you will see the failure pattern of a mix right there. Again, very high strength mixes fail in this fashion, as you would have seen. Now, when you look at the influence of fibers, this is a little tricky figure because the stress axis in kips per square inch, which is 1000 psi. So, I have put in the conversion factors also. So, the left top figure is the same one that I showed earlier, which is basically the axial strain and radial strain as a function of axial stress for unreinforced mixes, and the one on the left bottom is for a mix with 1% fiber. Also notice that the axial and radial strain axes are different, right. The first one goes only to 0.5, the second one goes to 1 for axial strain and minus 1.6 for radial strain. The axial strain is increased obviously because your effective fibers post first crack, and you will also notice that the maximum axial strain at the peak has not changed, it is still around 0.35, which means from a design point of view that is what you should use, because in reinforced concrete design you look at what is the strain at peak load. The radial strain, if you look at the left bottom picture, the radial strain has significantly increased with increase in fibers. Very easy to explain, because if you push in compression, because the fibers confining the movement, you can have much more radial strain without failure, because fibers are holding and bridging the cracks and all of that. On the right picture, you have the response of the mix with 3% fibers, right. You have much higher radial strain, you have strain is not dropping, stress is not dropping anywhere close to 0. Even at a radial strain of 1%, you have about 50% of your axial capacity still left in the specimen. This helps you to understand how you would use this idea of ductility in design. I will show you some tensile pictures also in a while. The other thing to notice, if you have 3% fibers, typically you expect strain hardening, right? But you are not saying, and typically when people talk about ultra high performance concrete, they said 3% steel fibers and our UHPC is strain hardening. But we are not seeing strain hardening, we are seeing strain softening. That is the trade-off that you make by the addition of aggregates. The larger aggregates, coarse aggregates, are known to give you deflection softening behavior because you create those interfaces around which cracks can propagate and the fibers are not very effective. But if it is a mortar where the size of the aggregates are very small and fibers can take into account the crack bridging much faster, if you do a mortar you will get deflection hardening. So then the other question is the trade-off, do you want a strain hardening UHPC or are you okay with a deflection or strain softening UHPC? If you want strain hardening UHPC, you go for UHPC mortars. If you are okay with, I am okay with some kind of a deflection softening, if not to a large extent, something like this, then it is not a brittle failure still, it is not a complete brittle failure, you still see there is some post peak deformation. So that is something to think of while you design this mix. Now slightly more different structural aspects to think of when you design this mix. What I have shown in the picture on the left top are the stress strain curves, but marking significant points the stress strain curve based on the strain relationships. So what I have in the bottom curve are the axial strain versus volumetric strain. Okay? So the response of axial versus volumetric strain. Volumetric strain is nothing but the axial strain plus twice the radial strain, and the volumetric strain you can use from simple transformation using Poisson's ratio and the principal stresses sigma 1 and sigma 3. And then the volumetric crack strain is a volumetric strain minus the elastic strain. Elastic is up to 50% of peak, is a random definition. Okay, so if you look at this, it is some very interesting points. You can see here the volumetric strain on the bottom picture on the positive axis, the overall volumetric strain, and on the negative axis of the bottom picture you will see crack volumetric strain, which is the total volumetric strain minus the volumetric elastic strain. Okay. Now if I take the point of volumetric strain of 0.05, 5% volumetric strain, and come to the volumetric strain curve, go up, hit to the curve on the elastic part, that pretty much is the first part, about 25 megapascal, around that range, where you are actually compressing, you are getting that increased stress because you are closing all the micro cracks within the specimen, right. You have some volumetric strain, positive volumetric strain, but then you are closing micro cracks in that specimen. Now if you go to that point, and this is a very significant point, if you look at that point where the crack volumetric strain tends to deviate from 0, the bottom point where it starts to deviate from 0, if you take it all the way up, you will get what is called the crack initiation stress, which is basically your end of linear elastic region. Now what happens, normally we do this all very randomly. You take the slope, you say that our slope has kind of look to change, you take it. In UHPCs you can't do that because the linear elastic range, because of the very high strength of the material, is much higher. Okay? So you have to actually have this kind of a transformation to understand where the crack initiation starts. So you can say about 50-60 megapascal you start the crack initiation strain, that is the end of linear elastic regime. So now I am not defining my linear elastic regime as 75% of peak stress like you normally do, or linear elastic regime as wherever the tangent intersects or whatever. It is basically now based on the idea of strains, the crack volumetric strains. More fundamental, more material response related rather than random fixture of points. So that is a crack initiation stress. And the other important point is a crack damage stress, where the volumetric strain reverses to dilation. You see that point marked 4 in the curve, where the volumetric strain starts to go back into dilation, right. The strain starts to come down, There the crack damage stress, volumetric strain, reverse dilation, you have unstable crack growth that is happening. So, that is crack damage stress. So, we call the crack initiation stress and crack damage stress as critical stress states for UHPC. Not like conventional concrete where you have only the peak strength or peak stress, you actually need these two stress states, because crack initiation very high, you are designing this material to carry extremely high loads and be very durable, and crack initiation is not what you want at very early ages. And crack damage, or the state where you have starting to have dilation, is the end of the load carrying capacity basically. So, sigma CD 125 megapascal is pretty much what you can theoretically use for design, because beyond that what you are seeing are the effects of loading. Okay. Rapid increase in volumetric strains and stuff, which is loading effect. So, you do not want to consider that. So, crack initiation and crack damage stresses as, and about 25% lower than peak stress. So, two different critical stress states. If you look at flexural strength, 20 to 25 megapascal flexural strength for these materials. If you have it, fiber reinforced, extremely high flexural strength. Effect of fibers, again you see fibers bridging the cracks, lot of fibers in flexural failure. We have done digital image correlation to actually look at how cracks propagate in these materials. It is a non-contact optical speckling method. You track the surface strains, and then based on that you figure out where the crack patterns are, and you take images at specific intervals very fast, and then you track the movement of every speckle. You do what is called a cross correlation analysis to find out what is actually happening. You can find out Lagrangian strain fields based on the movement of speckles. Basically it is like surface strains, right. A point moves from here to there, change in distance divided by the initial distance is a strain of that point, and you convert that into a Lagrangian strain field. Okay. So, just to give you a few important points in the load deformation plot. So, you see the top picture, stage A corresponds to just starting the loading pattern. You have almost no strain set up in the material. Whatever you see, those ping strains at the edges are of the compression of the loading support. It is not really the effect of loads, but you just start to see some patterns of strains emerge. Get to B is pretty close to the peak load, right. You will have some tensile stresses that you see on the bottom, more compression in the top. When it comes to C, which is at the peak, you will see a lot of, again this is a fiber reinforced specimen, that is why you will see a lot of deflection hardening here, and this is a fiber reinforced mortar, not concrete, that is why you see deflection hardening. At C, you will see in the tension zone of the beam, you will start to see some localization of strain, and actually if you go to point D, which is further down in the post peak region, you will see a lot of strains at the center point of the beam where you likely have formed a crack. So, I will show you a picture to actually show you how the crack pattern is emerging as a function of load. So, this is all the stages that I have shown you. Okay, you can see compression and tension, you see tension building up in the blue, you see those flames coming up at the bottom, right. So, those are all strains. When you start to see the red, can you see the crack there now? Right there, and then that red flame at the tip of the crack is actually a fracture process zone. So, if you theoretically calculate the process zone as some value of strain, now you can actually quantify what the process zone is and how the process zone changes with load, and you will see random cracking, you will see extremely high strains at different locations. Now, you can start again at the edges, I would not consider those are artifacts, but if I just zoom the portion under the load, I can now start to understand how actually a crack propagates in these materials. Okay, and then finally a few notes on durability. All of you know what rapid chloride permeability is. If I take a typical ordinary Portland cement concrete with a water cement ratio of say 0.4, you will get a value of about 4000 for RCPT, very common. If you do a high performance concrete, which means a water cement ratio of 0.3, 0.25 to 0.3, you will get an RCPT value of about 1000. Now, with ultra high performance concrete, you are getting to about 250 and 300, really low values of rapid chloride permeability. I just showed this test and this value rapid chloride permeability, you must have known in your classes, is not something that you should trust all the time, because anytime you change the pore solution conductivity with materials like silica fume, you have spurious effects with RCPT under high electrical voltage. So, part of it, you suddenly can't say this 20 times lower, meaning the material is 20 times better, the material probably is 5 times better, but this test actually exaggerates the effect when you have lowering of pore solution conductivity. So, but it is better as a quick screening test, not a bad option, but not a good test for real performance measurement. This test is a little better, actually quite a bit better, non-steady state migration using NT-Bill 492, where your actual application of voltage is lower than a rapid chloride test. The concentration of upstream and downstream solutions are also different. So, you basically have an electrical migration of chlorides, electrically induced migration, right? The ions are migrating. You talk about electrically induced migration of ions, but in any system, if you migrate ions, you forcefully push ions from one side to the other, the system by nature has to be electrically neutral. There has to be electroneutrality maintained in the system. So, for every one chloride that you push into the system, some negative charge should come out of the system, right, to maintain electroneutrality. What is the negative charge that can come out of conduits fairly quickly? Hydroxide. So, for one chloride that goes in, one hydroxide that comes out, right, and then sodium and potassium and calcium all do the remaining charge balance. Okay. So, in this state, so you carefully control the initial current and initial voltage in such a way that you apply that voltage for 24 hours or 48 hours or whatever, depending on the initial current, to find out how much of chlorides have gone through. You calculate a chloride diffusion or a migration coefficient. For an OPC concrete, you get about 10 to the power of 10 to the minus 12, 10 times 10 to the minus 12. For UHPC, it is about 2 times 10 to the minus 12, so about 6 times lower migration coefficient. Again, this is accelerated migration, which means you are making electric field push things through, so not a real representation of what is actually happening in the field. If you do a diffusion, natural diffusion test by ponding chlorides, you will see that the diffusion coefficient is about an order of magnitude lower. So, different tests will tell you different levels of where these materials stand. So, one test is not essentially an indicator of durability. You have to do a few tests to make sure that you get the spectrum of durability advancements, durability enhancements in the material rather than just one test. Sorption or water transport also shows similar relationships. You can do initial sorptivity, which is the water intake immediately after you put in first 6 hours, and then the long term sorptivity that you measure for 10 or 14 days. And you will see that the initial sorptivity is governed by the larger pores which can absorb a lot of water early on. The long term sorptivity is governed by some amount of diffusion also through the smaller pores in the material. It is not completely diffusion, you have not probably transformed into completely diffusion controlled regime, but it will give you a fair indication of the size of the smaller pores in the material also, which you can see the secondary sorptivity is much lower. And then cost analysis, just to give you an indication of costs, different values in dollars per US ton. Its US ton is 2,000 pounds, not 100,000 kilograms. So, dollars per 2,000 pounds, you see the cost of all of those materials. You will see silica fume, nano silica if you have, fibers are the most expensive components with $3,000 per 2,000 pounds of fibers, $1.50 per pound, reasonable. Superplasticizer costs about $15 a gallon. So, if I use all of that per cubic yard of material for different mixes that I have used, you will see that fibers constitute the highest cost, and that is what you pay for the ductility. And if you use mixtures without fibers, then the superplasticizer and OPC and the cement are the highest cost. You look at superplasticizer costing almost the same as that of cement. So, it is a very expensive mix. And then if you look at conventional, I told you about $2,000 per cubic yard for conventional commercial ultra high performance concrete. The mixes that we make and ordinary concrete is about 100. The mixes that we make are anywhere from 450, 500 to about $1,000. So, we are easily able to shave off half the cost. And for a Department of Transportation that is wanting to place 10,000 cubic yards, you can see the amount of cost saving compared to a conventional commercial mixture. So, that is why Lafarge makes a commercial UHPC called ductile, and that costs extremely high, and there are a couple of other UHPC manufacturers also. But lot of state departments of transportation are going towards non-proprietary mixes where we design it using. So, ours is a method that we have proposed as a standard, which has not come yet, but we are proposing this as a methodology where you can design ultra high performance concrete from first principles. Finally, I will give you one little note on design. There is going to be conventionally different design philosophy. The picture that you see on the left is a UHPC section with just fibers, just steel fibers, right. The immediate thing, do I have any change in my strain diagram? No, it is like exactly like conventional concrete strain diagram with 0.003 as the maximum concrete compressive strain. But I have changes in my stress block. What have I done is now below the neutral axis my concrete is not wasted. Below the neutral axis now I have a significant amount of tensile stress that is carried by concrete. Two different advantages here. One, if you really design a high strength concrete section, you will know that your neutral axis starts to shift up and a lot of concrete below will get wasted depending on what is the application of the beam. Now, you will not have that concrete wasted, you have a certain tensile capacity of that concrete that you can beneficially use. And the second one is what we call a hybrid reinforced section, where you have really a regular reinforced concrete beam with ultra high performance concrete that has fibers. Now, you have multiple effects. Again, in your area below the neutral axis, you have tensile contribution of steel, which is area of steel times the yield stress of steel ASFY, plus the tensile contribution of the fiber reinforced concrete, which you do a constitutive model for compression and tension. You can see that there. Constitutive model for compression is a bilinear curve, increasing compression, elastic, plastic, whereas for steel tension is a trilinear curve where you have an increase in tensile stress, a drop, and then a plastic region in the tensile zone, and you have different parameters. So, now with this you can start to design your sections much more efficiently and much more economically, so that you are using quite a bit of the advantage of concrete. Otherwise, if you look at the section, if you do not have steel fibers, more than half of concrete is wasted structurally, right. You have no use for it, but here you can start to use some of those advantages. So, the overall cost, the increase in cost can a little bit compromised, can little bit be accommodated by doing appropriate design strategies, and that is a topic for a completely different class. So, in summary, you have a multi-level particle packing approach both for the paste fraction as well as for the aggregate fraction. Paste fraction dictated by packing of particles and rheology, aggregate fraction dictated by what we say is a compressible packing model, but you can use any kind of packing model. You can have very high compressive and flexural strength, ductility is very high, durability is very high. We have done cracking tests, cracking propensity is low provided you cure them really well. There are issues with autogenous shrinkage which has to be very well controlled. This property can only be accomplished by a robust, rational mixture design procedure. You can't generally do a general mix design procedure using any of the standard available methods which are water cement ratio based mostly. You can't do that. Water cement ratio is basically a secondary parameter here. First is always packing. Water cement ratio is that which is required to make this thing flow and fill. You have to have careful material design to ensure it's economical, and then structural design modifications to account for significant improvements in tensile capacity. It's a tensile capacity and ductility that makes this material very different from conventional concretes. Finally, I have a bunch of references here for anybody wanting to look at more, and there are papers where we have explained the entire particle packing and mixture design philosophies and some reports from Federal Highway Administration that have explained the advantages of UHPC, where it is used, what's its life cycle benefits in structural engineering and all of that. Okay. Thank you very much.